Welcome to iLecture Online, and today we're going to do some problems involving Coulomb's law. So we're back in the realm of physics. And just as a reminder, here's the equation that describes the force that exists between any two charges called Q1 and Q2, depending upon the distance between them, r squared. Now K is a constant of proportionality, and K equals 9 times 10 to the 9th newtons meters squared per, not kilogram. I was going to write kilograms. Well, that's for Newton's law of gravity, but per Coulomb squared. Coulomb is the unit of charge. All right, so here's our problem. It says a 6 microcoulomb charge, and microcoulomb is 10 to the minus 6 coulombs, is placed at the origin, and a minus 4 microcoulomb charge is placed 2 meters to the right. What is the force on the first charge due to the presence of the second charge, and what is the force on the second charge due to the presence of the first charge? So, as we usually do, we want to draw a diagram so we can get a visual picture of how to do this problem. So let's draw a coordinate system. Here we go. There's the y-axis, there's the x-axis. We place one charge, and it looks like it's a positive charge, so we place a positive charge, call it Q1, and that's equal to 6.0 microcoulombs. Then it says we have a second charge to the right, so we place a second charge here. Now that's a negative charge, and we call that Q2, and that's equal to minus 4 microcoulombs. And now I should say minus 4.0 to be a little bit more accurate. Microcoulombs, there we go. And we need to find the forces on each other due to the presence of the other charge. So how do we do that? Where do we start? Well, the first thing you want to do is draw the vector diagram. So the vectors representing the forces. And so let's go to our first charge right here. And what would be the force on this charge due to the presence of this one? Now they're oppositely charged, and we know that opposite charges attract. That means that this force is this charge is being pulled to this charge, and so we can draw a vector this way. So call this F on 1. So let's call it F on 1 due to the presence of 2, or charge 2. Now also, since we also have to find what the force is on the second charge, we can go to this charge here and say, well, how does this charge influence that charge? And again, since they're being attracted, we can say that it's being pulled towards this charge. So we can draw a force vector this way. So this is F on 2. And of course, since they're vectors, we need to indicate that they're vectors. All right, so now that we have at least got a visual picture of what's going on, now we have to find the magnitude of this force F1. And so to find the magnitude, we can use Coulomb's law. And I'm going to get rid of a little bit of this line here. Give me some more room. There we go. So using Coulomb's law, we can say that the force on 1 is equal to K times Q1, Q2 divided by the distance between them squared. All right. Now we plug in the numbers. So this is equal to K, which is 9 times 10 to the 9th newtons meters squared per Coulomb squared, times the magnitude of the first charge, which is 6.0 times 10 to the minus 6 coulombs. The magnitude of the second charge. Now here you say, well, there's a negative there. Shouldn't I put a negative in? Well, the best thing to think about it is, let's just say that we write it like this, where we indicate that we're finding the magnitude of the force. And magnitudes don't have direction or signs, so we can just take the absolute value of that, and so write 4.0 times 10 to the minus 6 coulombs. Again, the sign doesn't matter here since we're simply finding the magnitude of the force, and then we divide the whole thing by the distance between them squared. Knowing that the distance between them here is 2.0 meters, we can write 2.0 meters quantity squared. And now I realize that I did not bring my calculator, so I'm going to be right back. Okay, back with my calculator. I can now go ahead and plug in these numbers. So it's 9 e to the 9th times 6 exponent 6 minus times 4 exponents 6 minus, and divide the whole thing by 2 squared equals, and pen. All right, so the result is 0.054, and of course the units are newtons because the meter square cancels out and the Coulomb square cancel out, so we're just left with newtons. So the magnitude of that force is equal to 0.054 newtons. Now, that's just the magnitude. Now we have to find the direction as well, because we also want to write the answer in vector format. Realizing now that the force on Q1 is directed to the right, and to the right is a positive x direction, we can then say that the magnitude of the force, or the vector quantity of the force, 1, is equal to 0.054 newtons in the x direction, positive x direction. So we can write the directional vector, unidirectional vector x, and this is a positive quantity now because we know it's to the right, and so that would be the answer in vector format. So that's the magnitude of the answer, and that's the actual answer. It's 0.054 newtons in the positive x direction. Okay, now for the second part of the problem, we're supposed to find the force on the second charge due to the presence of the first. So now we are dealing with this vector force right here. And again, we can say that the magnitude of the force, now we're looking for F2, is equal to K times Q1, Q2 divided by the distance between them squared. Now you realize here that we're dealing with the same quantities. We're dealing with the same two charges, same distance, same K. So we know that the magnitude of that force, F2, will also be 0.054 newtons. So we can see that the magnitude of the force is exactly the same, but the direction is different. Now we can see that the force is acting on Q2 to the left, so we can then say that F2, I'm writing 2 definitely in the wrong place. F2 is equal to minus, indicating the negative x direction, minus 0.054 newtons in the x direction, like so, and that would then be the vector answer or vector quantity answer for our problem. Okay, and that's how you do this. Now this is a simple example. Of course, things get a little bit more difficult when we start putting the charges in different places, not on a single line, so I'll show you some more examples where things get a little bit more hairy. All right, that's how you deal with Newton's or with Coulomb's law.